Okay, first question. A mixture is A, two or more pure whoops, I always forget that it doesn't default to let me write. Two or more pure substances. What do we call one type of element in a substance? Like if substance is made of only one type of element?
Like pure something?
It's elemental. Elemental if it's one type of element. If it's one type of molecule, then it's pure substance. Okay, three or more pure substances. Well, three or more would be included in a mixture, but a mixture is two or more, not three or more. Okay, number two, what happens to electrons in atoms during a covalent bond? They're shared. The co is your key there. They're shared. What about an ionic bond? What happens with the ionic bond? It's not so much they split. They transfer, yes. An electron is transferred from one to another. That's the way we say it, at least in a class at this level. You could have this ion was made this way, this ion was made this way, but then they're held together by the opposites attract electric force. Number three, measure the amount. A measure of the amount of dissolved solute divided by a solution is known as what?
Saturation.
Not saturation.
Composition.
Not composition.
Concentration.
Concentration. Now let's go over what these words are. So saturation is when you have as much solute dissolved as it can possibly hold. So if you put in more, it won't dissolve. It'll just sink to the bottom essentially. And so when we have 100% humidity, we actually have a saturation of the concentration of moisture in the air. Beneficence, that is not related to chemistry. Composition is how much of this you have and how much of that you have. And solvation is just the process of making a solution. Finally, which of the following does not affect reaction rates?
Antagonist, which is not even part of it.
Right, because once again, that was not part of chemistry. Yeah. Okay, now Annabelle asked about help with the homework. I had actually 3 people who contacted me asking if I could delay the homework again. I'm kind of torn. I want students to, be able to do their best, etc. But at the same time, the homework has been available for a week, and the stuff that it's over, we finished talking about on Friday. And so, there's been plenty of time. So, like I said, I'm torn here. What good reasons are there for it to be delayed?
Because we asked.
I know for me personally, I have been dealing with financial things, and that has been really stressing me out, so I'm not getting anything done. But that doesn't mean that I should make up excuses. So I know that falls on me, like that's my issue, but yeah.
Yeah. As you probably recognize, as a teacher, it doesn't hurt me to postpone it, right? It's, as I say, no skin off my back. It is just integrity of the classes we teach, and it's something that all of you will be facing as you become teachers. What to do. I will once again extend it, and then add that I won't do that again. Okay, so this will be the second and last time that I'll extend it. But I will extend it to being due Thursday night instead of Wednesday night. Okay. Now, what question did you have you wanted to talk about, Annabelle?
Number 11.
Okay. It takes an act of God for me to get signed into this thing with yeah. Because it automatically wants to change everything for me. It'll be there. Yay. Come on. All right, so here we go, number 11. So number 11 is about balancing equations. So like we talked about in class on, what did we talk about balancing equations?
Yeah, that was Monday.
What was on Monday? Okay, so we did, 17 is Monday, so there was some stuff that wasn't talked about Monday. When we balance the equations, what is the key thing we're trying to do?
Keep the numbers the same.
First, oh boy, now it's not giving me my tools to write. Well, in that case, I'm going to just copy this and go to this app. Okay, so here's the problem. Balance this equation. We need the same number of each type of atom on each side of the equation. So if we look at the first equation, we have iron. Fe is iron, right? You don't have to have that memorized. What does the parenthesis S mean? That's not something we've talked about, so that's going to be kind of guesswork. What do you think the S means?
There might be multiple of it, like it's in plural.
That would make sense, but it's not it. It means solid. It's telling us the phase it's in. And so then we have plus O2 with the G. If S is solid, what would G mean?
Yes.
That's a good guess. Did you say gas? Did you say gas?
Yeah.
Oh, that is correct. I thought you said guess. I was like, well, sure, that would work. So S is solid, G is gas, AQ is aqueous.
Yes.
So it's just telling us what form it's in. It doesn't affect our solving this. So we have iron that's Fe plus O2, and that makes Fe2O3. So we need to match these up so we have equal numbers of iron and oxygen on both sides. So,
Question.
yeah, go ahead.
How are we supposed to show this on our homework?
You explain how you got there.
What I
Okay, so we'll do the first one. I'll tell you how, okay, Annabelle? So when I look at this, I know that I have to have at least 2 irons because there's Fe2 on the right-hand side. So I might make a first guess that it's 2 Fe plus something O2 yields Fe2O3. But then how many O2s would I have to get 3 O's?
I couldn't make them up.
No, this is not right yet.
Oh, okay.
Yeah, this would be an incorrect. What would I have to multiply the O2 by?
Wait, can you just do correct them?
Well, I was hoping that you'd learn how to do these. That's why I'm explaining. Right. It's not just being able to get the answer, it's being able to do it again for parts B, C, and D.
Well, yeah, but it's not what we need to do.
This is the method that's correct. So if I have 2 irons, then my irons match up. And now I need to get my oxygen so those match up. I have 2 on the left side and 3 on the right. So how many O2s do I need to get to 3 oxygens?
Well, you multiply times 2 to get 6. So
Okay, so if I multiply by 2 to get 6, then I would have,
no, by 3.
yeah, 3 actually would give me 6.
And then 2 in front of the other one.
But since this is 2 and this is 3, if I multiply this by 3 halves, then it would be balanced. Then I would have 2 irons and 3 oxygens, 2 irons.
Do we have to do fractions though?
I'm not done yet.
Oh,
This is the method for solving it. So then it would be balanced, but the problem is we have a fraction. And we can't have a fraction, so the last step is I have to multiply everything by 2 to get rid of that fraction. And so 2 times 2 is 4. 2 times 3 halves is 3. And of course, 2 times 1 is 2. And so now finally, how would you show that you're correct? You would make sure. Irons, I had 4 on this side, and 2 times 2 is 4 on that side. Oxygen, I had 6 on this side, 3 times 2, and I had 6 on this side, 2 times 3, and so it's balanced. So that's the method to go through to get to your balanced equation. Now, sometimes you can do it by inspection, but if you do it by inspection, still make sure you show this, show that you've tabulated so it's balanced. Fire away.
So I write down how many of each, like on each side there is. You know, I write the number beside it, and then I do. Is it three times counting factor? Is that the word I'm looking for?
Yeah,
Is that acceptable? Can I do that?
yeah.
Okay.
Yeah, that's, I just, as long as you have a method that works, it's great. I mean, you could have also done, A times FE plus B times O2 is C times FE, and you could have made linear equations and solved those linear equations.
Yes.
Okay, since we're 15 minutes in, I'd better get to the actual lecture part of the lecture. And if you have more homework questions, ask about them in lab tomorrow. We can spend more time in the homework in lab since I postponed it for a day. So today we're going to talk about acids and bases. I'm sure you've heard of acids and bases, and you have some knowledge of acids and bases, although that knowledge is, I assume, fairly limited. So, okay, I'm actually not going to ask Vanessa because she obviously has a lot of chemistry knowledge already. What did the rest of you know about an acid?
Is either something that had like a high pH level or it was a drug. We don't want to know.
Okay, something that has a certain pH level or there's a drug called acid. Anything else, like what happens if you wash your hands in acid?
It's gonna burn.
It's going to burn. That's going to be bad. Well, it depends on the acid, but it can be bad if it's a strong acid. What about bases?
Could those also burn?
Actually, they don't. They feel very slippery, but they really don't damage you. At least that's my understanding. So that's what we're going to learn about here. So examples of acids, citrus fruit that I love is acidic. Pickles. Well, actually, I know those are acid. Pickles, I'm trying to remember. I believe everything on top is acid. Sodas are definitely acids. They're like phosphoric acid. Nobody worries about getting burned from drinking a soda. Do you?
No, no.
Or getting it on your hands. Toilet cleaner. Have you guys seen memes saying that you can clean your toilet bowl with Coca-Cola?
Yeah,
You know why?
because it's acidic.
Because it's an acid. It's a stronger acid than your toilet bowl cleaner. So probably going to do a better job. Except for that caramel coloring will probably cause some discoloration. So those are acids, examples of bases. Baking soda is a base. Soaps are bases. Drano is a base. So those are some common acids and bases that we see. Here is a mnemonic that you really should memorize. Bad. Bases accept protons. Acid donates protons. It says that at the bottom. This is the Bronsted-Lowry definition. There's different definitions of acids and bases. So this is one of them. A base accepts a proton, an acid donates a proton. Well, what is a proton?
Like a positive charge.
It's like a positive charge. It's the nucleus of a hydrogen atom, right? So I actually have a slide here to make sure we know. The hydrogen atom, a proton, an electron. If you take away the electron from the hydrogen atom, what do you have?
Just a positive charge thing?
You have just the hydrogen ion, the proton. And so with that definition, that a base...
So hydrogen is acidic?
Well, the hydrogen is the key. If you have a reaction and a molecule gives up a hydrogen ion, so it keeps the electron, just gives up the proton, then it's donating, so it's an acid. Right, so bases accept. If you have a hydrogen ion that's added, then it's a base. If it gives up a hydrogen ion, then it's an acid. Yeah.
I'm going back to the first, like a base accepts something like.
The one with the mnemonic?
Yeah.
Okay, can you give an example?
We have lots of them, yes.
We're good.
Okay. So here's the final definitional stuff, things before we get to examples. An acid donates a hydrogen ion. Acids tend to have sour taste. In fact, the name acid comes from the Latin word for sour. And bases, they accept the hydrogen, they have a bitter taste, they feel slippery. We often call them alkaline, and that means ashes, because you have a lot of ashes are basic. Okay, so examples. HCl and H2O. If you mix them together, you will have the hydrogen that was on the Cl. The hydrogen that was on the Cl moves over to the water. And so you have the missing hydrogen here and the extra hydrogen there. So with our mnemonic, bases accept and acids donate. Which one donated a proton? Donated an H plus. The chlorine gave away its H plus. It kept the minus, so that's why it has the minus sign here. And so the chlorine donated. So HCl was an acid because it donated. Which one accepted the hydrogen? The water. So base accepts. So in this case, water is the base, and HCl was the acid. In fact, we call it hydrochloric acid. HCl, we don't just call it hydrogen chloride, we call it hydrochloric acid. So
Wait, they accept what? Neutron? Wait, what are they?
it was protons. Remember, that goes back to that mnemonic where I had protons. I wrote it in small red letters at the bottom. It was written in all capitals, blue letters. So there's an example of a reaction. Notice this arrow. This arrow says we started with HCl and H2O, and we ended up with Cl minus and H3O plus. What do we call as a group these things here?
The reaction?
The reactants. You were close enough that I'm going with it. The entire thing is a reaction. The things that we started with are the reactants, and what do we call the things we end up with?
The product.
The product. I'm going to put S because there's two of them. So that arrow tells us which side is the reactants and which side is the products. And we were able to identify which one was an acid, which one was a base by following the hydrogens. A second example. I told you, Vanessa, I had many examples here. We have H2O and NH3. What's the common name for H2O? Water. What would its standard name be? Yep, dihydrogen monoxide. What about NH3? Do you know what its common name is? Okay, you could call it trihydrogen nitride. That would be its standard name. Its common name is ammonia. So we have, I'm not going to write it out for water. We have water and ammonia that are mixed together. Following the proton, which of these donated a proton? The hydrogen atom without its electron is the proton. So which one donated a hydrogen ion? The water did. So remember, with our mnemonic, the one that donates is the acid. So water is the acid. And which one accepted the proton? The ammonia. So the ammonia was the base. But let's compare this with the previous one. In the previous one, water was the base and HCl was the acid. Now we have water's the acid and ammonia is the base. What is a little confusing about the comparison of these two?
The water changed.
The water was an acid in one and a base in the other. Water can be both an acid and a base, depending on your reaction. Oh, one more thing. This is just showing the reaction in the reverse direction. This here is called ammonium. So the difference in ammonia and ammonium is the one that ends with the UM has an extra hydrogen. So now the reaction is going the opposite direction. It's the same equation, except for the arrow is reversed. So now we have our reactants on this side and our products on this side. So since the reaction is going to the left now, which of the things on the right is going to donate a proton?
Ammonium donates.
Do bases always accept
That's the Bronsted-Lowry definition, that bases accept protons. So yes. Okay, so ammonium is going to give up one of its hydrogens, and it's going to be hydrogen ion, so it becomes neutral. And so ammonium, because it is donating, is the acid, and the OH is going to accept. And so the OH is, in this case, the base. Now, this same reaction was shown going both ways. This is actually the way it is with chemistry. You mix things and they move to an equilibrium state. If you had higher concentration of one thing, it'll go one direction. Higher concentration of the other, it'll go the other direction. And so we generally will write the equation like this, where we have arrows going both directions to indicate that it will reach an equilibrium between these. And so for the left-hand side, water was the acid and ammonia was the base. For the right-hand side, the hydroxide ion, this thing here is hydroxide, was the base, and the ammonium was the acid. So it depends on which side of the equation you're looking at, which one you call the acid, which one you call the base. So our first of the Wu class, I'm sorry, I don't have it started. Start. Okay, and remember it's www.wuclap.com/SCNC111. When water behaves as an acid, what does it lose? Two answers. We have three answers now. All right, all four of you. Thank you. And we have three that said a hydrogen ion and one that said a hydrogen atom. Okay, so the only difference here is the word ion versus atom in the answers. What does it mean to be a hydrogen ion versus a hydrogen atom? What distinguishes the two of those? What distinguishes between a hydrogen atom and a hydrogen ion?
The ion does not have an electron.
No electron, therefore it's an H plus. This has one electron, it's a neutral H. When we're talking about the acids and bases, it's about donating a proton or a hydrogen atom. And so the three were correct, or hydrogen ion, I just said it wrong. The three were correct, it's a hydrogen ion that's being donated. The electrons are staying put. It's just the hydrogen ion, the proton, that's moving. A salt. Everybody knows salt, right? What is salt to you? You put salt in your food. What is it?
Flavor, like a spice.
Okay, like a spice, a flavor. As a kid, I always thought of salt as NaCl, sodium chloride.
Seriously?
Yeah.
As a kid?
Yeah. The sodium chloride. Sodium chloride is an example of a salt. It's not the only salt. And when you buy table salt, it's not always pure sodium chloride. If you look at this example that I have, it says there iodized salt And potassium chloride,
Does it also have the thing that keeps it from getting wet or stay together or something like that?
it is going to have an anti-caking element as well, probably something like titanium dioxide. So iodized salt. Any idea what iodized would mean? Just guessing? Well, if you look at the periodic table, which column is iodine in?
What's the word for that? Is that I?
Yes, I.
Oh, no, so
It's one away from the noble gas. It's in the halogens, right. Where's chlorine? It's the halogen. So if they're in the same group, they have the same electronic structure for the valence electrons, and thus they basically behave the same chemically. I say basically, they're not exactly the same. And so the iodine can replace the chlorine. Just like in your homework problem where it asked about calcium being replaced with strontium. Calcium and strontium are both alkali earth metals, and so they're going to behave the same, and one can replace the other. And so the iodized salt is sodium iodide. That's also a salt. So it's not like they're lying when they call it salt. And then it says potassium chloride. Potassium is the letter K. That's one that you kind of have to know or you're not going to guess, right? Nobody. And so potassium chloride is also a salt because potassium is in the same column as sodium. Chlorine, of course, is there. So this contains all three of those salts. A salt is a general term for the ionic compound that's formed when you mix an acid with a base. So a very common acid is hydrochloric acid. A very common base is sodium hydroxide. If we mix these together, what do you think is going to happen? What does an acid do?
Oh, the acid donates proton.
It donates a proton. So I'm going to have a Cl minus, and I'm going to put the proton just hanging out by itself for now. What does a base do?
It accepts the proton.
It accepts the proton.
You're going to have an AOH2.
Well, I'm going to write this like this, and then it's going to go to the OH2 just becomes a water molecule that hangs out by itself, and it drops the sodium. And then finally, these two are ionically bound together, sodium chloride plus H2O. So if you mix equal amounts of sodium hydroxide and hydrochloric acid, you will have a reaction that will give off some energy and produce just salt and water. So you make salt water. And so that is how all salts are formed. You mix an acid and a base, and you form water and a salt. So here's a table of examples. Hydrogen cyanide. You've all heard of that. You ever heard the phrase, drink the Kool-Aid?
Yeah.
That phrase didn't exist until I was in grade school, and Jim Jones had his People's Temple that had moved to Guyana, and they committed mass suicide by drinking Kool-Aid that had cyanide in it. This compound here, the hydrogen cyanide. So whenever somebody says drink the Kool-Aid, that means you're drinking the poison. Just giving you a little cultural perspective because it's cyanide. So you mix cyanide with sodium hydroxide, and the acid, what does the acid do? What makes it an acid?
It donates a proton.
Yes. So the acid donates a proton. So this hydrogen without its electron comes over here. And then you're going to form a compound, a salt, that is the CN and the sodium. So sodium cyanide plus water. And then we have nitric acid, NO3, HNO3. It gives its H to, in this case, we have potassium hydroxide. And so you form potassium nitrate and water. Hydrochloric acid and calcium hydroxide gives you calcium chloride. So everything here is a salt because it's the ionic compound that forms when you mix the acids and the bases. For every pair of acids and bases, you're going to have a different salt. Here is one that is near and dear to our hearts, probably. When you get a cold, you like to take something like pseudoephedrine. Why pseudoephedrine instead of ephedrine? Okay, I've never watched Breaking Bad, honestly, so I don't know exactly what they do there. But my understanding is they cook meth. And you start with, well, ephedrine, basically. Pseudoephedrine can be used to get to meth as well. It's just a little harder. And so that's why you have to have prescriptions and stuff for this to keep people from converting the over-the-counter drug into a methamphetamine to give people and mess them up. So when you go look at your little pseudoephedrine, you usually see something that says like pseudoephedrine hydrochloride. And so it's this here that it says for its active ingredient. Pseudoephedrine hydrochloride is a salt. It's a salt because it's the result of mixing an acid, in this case, hydrogen chloride, otherwise known as hydrochloric acid, with a base, the pseudoephedrine. And so if you look, the hydrogen in hydrogen chloride went off as an ion, and it attached to the negative electron pair. What kind of molecular bond would this be if I have a hydrogen ion attaching to the neutral nitrogen?
I literally have no idea.
Okay, it starts with ionic, but the molecular bonds were all blank dash blank. So it's ionic, and that nitrogen, notice it has the two lone pair electrons. It has a negative side where the two lone pair electrons are. That's what those two dots mean. Not covalent, that was between atoms to make a molecule. But here we're talking about between molecules. So it's an ion, and what do we call it when we have the electric charge not uniform, a dipole? So this is forming an ion dipole bond to hold that hydrogen in place for the pseudoephedrine hydrochloride, for the salt. All with me? Okay. What salt forms from the reaction of hydrogen chloride, HCl, with potassium hydroxide, KOH? So what's the salt? Got 3 out of 4. All right, we got already answered. We had 2 that said KCl, 0 that said this, 1, 0, 1. So let's start with the obvious. How many sodiums do I have on the left-hand side of this equation? There's 0. So it can't be sodium chloride because there's no sodiums to create sodium chloride. Yes, sodium chloride is a salt, but it cannot be the salt here because there's no sodium to begin with. Just looking at the numbers, we had 2 H's, we had 1 chlorine, we had 1 potassium, and 1 oxygen. If we go on this side, so far we have 2 hydrogens, 0 chlorines, 0 potassiums, 1 oxygen, and of course, still 0 sodiums. So what are we missing? We're missing a potassium and a chlorine. And then that balances it. So the salt that's formed here, potassium chloride, which was one of the salts in that Morton light. What makes the salt a light salt, by the way? It's light on sodium chloride. More specifically, it's light on sodium. Relative strengths. This was something that Alex alluded to right at the very beginning when I asked about what you know about acids and bases. And so strong acids and bases will completely ionize in water, but only really strong ones. Ones that aren't so strong won't completely ionize. So a weak acid, if you look in this picture, you have some that are ionized and some that aren't. So actually, that was hydronium. That was the wrong thing. There is not ionized and there is ionized for the acetic acid. Question? Okay.
So I found out why I am not getting my homework done, and it's because on my noodle, I only have homework 5.
Yeah, we're in chemistry section now.
Oh my goodness.
I'm sorry.
Oh, it's okay. It's all good. Yeah.
Yeah, I have it broken down into the material by topic /test.
Okay.
So weak acids don't completely ionize. You're going to have some of the acid and some of it that has, donated a proton. And so have you guys ever seen an example with a potato or a grapefruit used to make a battery?
I've seen a lemon.
A lemon, good enough. That's possible because you have the acid. A battery is not the right word, by the way. It's a voltaic cell. A battery is a collection of voltaic cells together. But you produce nothing if you put it in a non-acidic solution. You put it in a weak solution, you'll produce some reaction. You have some light there. Put in a strong acid, you'll have a bigger reaction. The chemical reaction that is powering that light bulb is an acid-base reaction. Now, we've already seen that water can behave as both an acid and a base. And so if you have pure water, the fact is you're going to have some of that pure water has turned into OH and some of it's turned into hydronium. So it's really kind of both at the same time. And so how we measure an acid or base is by measuring the concentration of hydronium. This here means concentration. The unit of concentration is M, which we saw before. 1 M means 1 mole. In this case, it'd be of H3O plus per 1 liter of solution. And we call that a 1 molar solution. So if this is 10 to the minus 7, it's 10 to the minus 7 molar solution. That's what we use to determine if something's an acid or base, is the concentration, the molarity of the hydronium ion. Now, if you notice this number, the concentration of the hydronium ion is really small, 10 to the minus 7. And simultaneously, the concentration of hydroxide, OH minus, is 10 to the minus 7, because if you had pure water, for every hydronium made, a hydroxide was made. Well, to get to the actual pH, we take this number, the concentration of H3O plus, and we take the log of it. And my next slide talks about the logs. So I'll go to the next slide. It's actually minus log. I forgot the minus sign. Log of a number. If I take the log, it's inherently log base 10. It's implied it's log base 10 if you don't say what the base is. What that means is, what would I have to raise 10 to get the thing in parentheses? So what would I have to raise 10 to get 10 raised to the minus 7? It's a silly question. I'd have to raise 10 to the minus 7 to get 10 to the minus 7. So that means log base 10 of 10 to the minus 7 is just minus 7. And so the pH of pure water is minus the log of the concentration of hydronium, so minus, parentheses, minus 7 or plus 7. So we consider a pH of 7 to be neutral, neither acidic nor basic, because it's the concentration that you have in pure water. If you have more hydronium, so let's say you had 10 to the minus 6 was your concentration of hydronium. Is that going to be a stronger or a weaker acid if it has more hydronium? The pH is lower, and lower pH is more acidic. Because it has more hydronium, it's more acidic. So if you had 10 to the minus 6, then you would have had the pH is equal to minus log of 10 to the minus 6 equals minus 6 equals 6. So a pH of 6, a pH of a number that's smaller than 7, is an acid. If it has something that's bigger than 7, so a pH of 9, then it's a base. So I will end with this slide that just shows you that if the hydronium goes up, the OH goes down. So acids have a lower pH, higher concentration of hydronium. Bases have a higher pH, a lower concentration of hydronium. All right, have a great day. I'll see you in lab manana.